If we've got a mass floating between two parallel plates, the concept behind that is it's all forces. Analogy-wise, if we compare this back to springs, this would be kind of like when we hung a mass from the end of a spring. If we wait for it to stop moving, gravity's pulling it down, the spring force pushes it up, and it just sort of stays at that position. Similarly here, if we were to draw a free body diagram, gravity's pulling down that little object. The electric field is creating a force on that charge that's pushing it up. So the electric force is up and gravity is down. If it's just floating, that means those two forces have to be equal. If one of them were bigger, it wouldn't be floating, it'd be accelerating up or down. We know that gravity is always m times g. Electric force is connected to electric field. It's Q times E. To emphasize that that's field, I'm going to put the little vector hat on there. Later we'll have to contend with electric energy, so capital E's are going to get a little bit confusing. We have one equation for parallel plates. We know that the voltage is equal to the field multiplied by the distance between them. If we flip-flop that around, the field is voltage over D. Combining those two, we get mg equals q volts over D, or mgd equals q volts. That's not an uncommon endpoint when we're looking at parallel plates and floating something. So mgd equals q volts. I'll always rederive it when we need it, but now that we've got it, it's just a matter of plugging in our numbers. We know the D is 1 centimeter. The voltage was given as 24 and the mass was given as 0.2 grams. So plugging that into our equation, actually I'm going to flip-flop things around. Q equals mgd over volts. 0.2 kilograms is 2 times 10 to the negative 4, or 0.2 times 10 to the negative 3. G is 9.8. The D was 1 centimeter, so that's 0.01. All over the volts I made up was 24. Multiplying that out, dividing that out, we get a charge of 8.2 times 10 to the negative 7. Before we leave this one, we're not quite done yet. One last little thing. If we connect the battery that way, negatives are going to get pushed into the top plate and drawn out of the bottom plate. The bottom plate becomes positive, the top plate becomes negative. Based off of that, the charge that would float in there is a charge that repels away from the bottom plate. Something that repels from a positive plate must be a positive charge. So just for completeness, let's emphasize that it's positive. That is